Sketch, now with this question here, we notice that the power in the numerator is higher than that in the denominator. When this happens, you will get oblique asymptotes. Look, this is really part of the extension 2 course. However, I think we should still just do one, all right? Okay, let's start with our y-intercept. You put x is 0. What is the y-intercept? It's y is 0 over 0 minus 4, it's 0. So, in other words, when x is 0, we've got 0, 0 as a point on the curve. Let's look for any vertical asymptotes. That's entirely based on the denominator. Vertical asymptotes will occur when x squared minus 4 is 0. We can factorize that out to x minus 2x plus 2. So we've got vertical asymptotes at 2 and negative 2. Okay, so this is what we've got so far. Just do it over here. It cuts through 0, 0. We've got asymptotes at 2 and negative 2. If you want, you can do the substitution on either side of the 2 and negative 2 now. Tell me, is it odd or even or neither? Is it an odd function, even function, or neither? Neither, because you've got an odd and an even power. All right? Should be, I don't think, or it could be odd, sorry. Actually, it could be, sorry, I shouldn't say that. We don't know yet, so we haven't checked it. All right, next, what are we doing? First derivative, y dash is vu dash minus uv dash over v squared. So u is 2x cubed, u dash is 6x squared, v is x squared minus 4v dash. So we should have v x squared minus 4 times 6x squared minus 2x cubed times 2x, is that right? Over x squared minus 4 squared. So you're taking out a common factor or are you expanding? I think I'd like to take out a common factor because I can take out 2x squared. Then I get 3 bracket x squared minus 4 minus, what do we got? 2x. Is that right? No, 2x squared again. That's a squared. Can I just check my first derivative with you, please, girls? I'm getting 2x squared times 3x squared minus 12 minus 2x squared. I'm getting 3x squared minus 12 minus 2x squared. Did you get negative 24x squared? Because that's just, no. Sorry. X squared minus 12. Is that right? Over x squared minus 4 squared. Okay. Is that what we got? For stationary points, y dash is 0. So 2x squared times x squared minus 12 over that is 0, which means that only the numerator can be 0. Which means that x is 0 or x squared is 12. We okay with that? X is plus or minus root 12, which is plus or minus 2 root 3. Now, root 12 lies between root 9 and root 16. Its value is approximately 3.3, 3.4, something like that. Right, let's work out the y values. We know that when x is 0, y is 0 from above. When x is positive 2 root 3, y is 2 times, I might just keep it as the root 12 actually, 2 times root 12 cubed over root 12 squared minus 4, which is 2 times 12, that's 24 root 12, which is 48 root 3. Over 12 minus 4 is 8. I'm getting 6 root 3. Is that what you got? 6 root 3? Because I'm getting root 12 cubed is root 12 squared, which is 12. 2 times 12 is 24, but we know that root 12 is 2 root 3. And when x is negative 2 root 3, you get, I think it's going to be the same except for negative. Is that right? When we look at this first derivative, it's a little bit complicated because we've got, if you're going to try the second derivative, you really need to expand the numerator. Otherwise, you're going to get, you can't do a differentiation with a combined product and quotient rule. All right? It's just too messy. Do a bit of work here. I'm just going to check with the first derivative anyway. So, and then we will do the second derivative as well to check for inflections. So, with the first derivative, I'm going to substitute into the first derivative. So I've got x and y dash. So, with the first derivative, when x is 6 root 3, we know that the first derivative is 0. I'm just checking the nature of the stationary points with the first derivative. So here is my first derivative, something less than 6 root 3. Now, 6 root 3 is approximately, you've got to give me a value for it, please, girls. It's 10.4. So I'm going to do approximately 10 and... Oh, sorry, the x is 2 root 3. I'm sorry. Sorry, ladies. It's 2 root 3, which is approximately 2 times 1 point... What's 2 root 3, girls? No, it's not 12. It's 3 point something. So I'm doing 3 and 4. I'm doing 3 and 4. Derivative. We're just looking at first derivative. We know that because I've got y dash. So when x is 3, I've got 2 times 3 is 12. 9 minus 12 is negative 3. So it's 12 times negative 3, which is negative 36 over 5 squared. What did I say? Negative over 25. It's negative. 0 gradient. We're hoping here we've got a positive gradient. We've got 2 times 16 is 32. Actually, 2 times 16 is 32. Then we've got times 4, 64, 128 over, this will be positive. 16 minus 4 is 12 squared is 144. This is a positive gradient. We've got a minimum at 2 root 3, 6 root 3. Sorry, this is when x is 2 root 3. So we've got a minimum there by substituting into the first derivative. And when x is negative 2 root 3, the substitution should be easy. Hopefully it's just a matter of changing sign. Why don't we do, it'd have to be negative 4 here and negative 3 on that side. Make sure you get that right because it's approximately negative 3.4. Negative 4 is lower. Otherwise, you're going to get the wrong gradients. So negative 4 should give me the same answer as positive 4. Do you see that? They're all x squareds. So I should get 128 over 144 there. And I should get negative 36 over 25 here. And I've got a 0 gradient there. So positive 0, negative gradient. We've got a maximum at negative 2 root 3, negative 6 root 3. When x is 0, looking at the first derivative on each side, I'm just going to do some nice easy values like negative 1 and positive 1. They're much easier to substitute. I've got this first derivative over there. Well, negative 1 and positive 1 are going to give me the same answer. Can you see already? We're substituting into x squared. So let's just do the positive 1. So it's 2, actually, yes it is. 2 times 1 minus 12, it's 2 times negative 11, which is negative 11, over 1 minus 4 is negative 3 squared is 9. You will get the same here. So this looks like negative gradient, 0 gradient, negative gradient. This looks like a horizontal inflection. Yes, negative 22. Horizontal inflection by the looks of things. Now, but you have to check for concavity change. Well, the gradient does show me concavity change. Look, concave up, concave down. Okay, while we're here, let's just do the second derivative anyway to check for any inflections. This is the first derivative. Y dashed is 2x squared times x squared minus 12 over x squared minus 4 squared. You cannot differentiate it in this way because you've got a product here on the numerator. So we're going to expand and get 2x to the power of 4 minus 24x squared. Now this can be differentiated. U is 2x to the power of 4 minus 24x squared. U dash is 8x cubed minus 48x. V is x squared minus 4 all squared. And V dash is 2 bracket x squared minus 4 to the power of 1 times 2x, which is 4x times x squared minus 4. Now we can do the second derivative. Look, in a HSC exam or something, they may say you don't have to find inflections or something like that. We've got a horizontal inflection anyway, but let's just see how we go. So we've got VU dash minus UV dash over V squared. So we've got x squared minus 4 squared times U dash is 8x cubed minus 48x. Probably should have taken out a factor there. I might still do that. I'm going to do that actually. Can I have the liquid paper, please? I'm going to make this 8 bracket x cubed minus 6x. Actually, why don't I take an x out as well? Might do that. Come back up here. Just to make it easier to factorize later. Otherwise it's going to be too hard. So, whoopsie. Oh, jeez. Right. Facebook. Oh, what was that? I don't know. Okay, 8x, x squared minus 6. I'm going to do that. So, times 8x, x squared minus 6. Hopefully that's right. Minus u. I'm going to factorize that too. 2x squared, x squared minus 12. Just going to make it easier. 2x squared, x squared minus 12. Where's v dash? Down there. Times 4x bracket, x squared minus 4. It's a bit messy. Over x squared minus 4 squared squared. Don't forget to squared. Because it is squared and then you're squaring it. It's v squared. So let's go. Factorize. Let's look at the x's. Oh, 8x can come out. What else? Yes. Look. 8x, 4x times 2. No, 8x. What else? X squared, one lot of x squared minus 4 can come out. Right, bracket. It's a bit messy. Then we've got another x squared minus 4 and an x squared minus 6. Very messy, actually. Really bad. Minus, is it minus? Yes. 8x squared is out, so we've still got another x and an x squared minus 12. Is that it? It is terrible, which is why we always know and remember how to do the first derivative and substitute on either side of the first derivative to test, to tell what type of stationary point it is. See, what might happen in this, if this is a question, they might say you don't have to worry about doing the inflections, even though we've got a horizontal inflection. But we can, in our horizontal inflection that we saw, we can see the shape. So what we could do back here, just one sec, you know how the curve goes like this? I can see a concavity change there, can you? Concave up, concave down. Do you know what I mean? There is concavity change. Yes, so can you just you could also say concavity changes. You can say on the left-hand side, on the left-hand side of x is 0, you've got concave up. Can you see that? And on the right-hand side of x is 0, I can see concave down when I do my gradients. I know I've drawn it like that, but it will be like that. Anyway, look, you'd only do that with a very, very complicated second derivative. All right, let's keep going. This where?
The x before the x squared minus 12. I think it needs
Yes. Thank you. That's right. Yeah, I was missing a squared. So we've got 8x, x squared minus 4. Let's expand. This is a mess. I've got x to the 4 minus 6x squared minus 4x squared, which is minus 10x squared, plus 24. Oh, good. Minus x to the power of 4 plus 12x squared. Oh, good. We get some cancelling. Over x squared minus 4 to the power of 4. Looks like, yeah, we'll cancel denominators. The x to the power of 4's go. So we've got 8x. That can cancel with this. And then I've got the x to the 4's go. I've got 12x squared minus 10x squared is 2x squared plus 24 over x squared minus 4 cubed. Oh, that's better. You could take out a 2, which is 16x, x squared plus 12 over x squared minus 4 cubed. All right. Now, remember, we've already worked out the nature of those other stationary points. We are actually going to get, we should get, when x is 0, we should get x is 0 as a solution here. But no, and the root 12s. Oh, yeah, it does. Good. Thank you. Sorry. So, for inflections, we already saw, we know that x is 0 is an inflection, you know. So, for inflections, y double dash is 0, which means it's 16x, x squared plus 12 over x squared minus 4 cubed is 0. We know that only the numerator has to be 0. We already know that x is 0 and x squared is negative 12. That has no solution. We already know that we have the possible inflection at, well, we already saw we had a horizontal one anyway. So if we just double check the concavity around x is 0, here is y double dash. Let's have a look. Our nearest stationary point's a fair way away at, wait, we've got asymptotes at 2 and negative 2 vertical ones. As long as we don't go anywhere near those, and as long as we don't go near 2 root 3, we're fine. So I'm going to go negative 1 and 1. So wouldn't this be negative? That would be positive, and that would be negative. I think that's positive. That's 0, and if you substitute x is 1, you get positive, positive, 1 minus 4, negative 3 cubed, negative. Negative. We already saw that before. Concavity change. Therefore, we've got a horizontal, we know we've got the horizontal inflection. Anyway. All we need to do is draw this. Look, there are no other inflections anyway. No other inflections. We already picked up the horizontal inflection. We've got vertical asymptotes at 2 and negative 2. So let's work out where the, you know, the behavior. So we're just now looking at behavior around asymptotes now. So at vertical asymptotes, x is 2 and negative 2. Let's have a look. X is 2. We're just looking at the values of the function here, not y dash, not y double dash. And then we've also got at negative 2. Now remember at 2 root 3, we've got turning point. Oh, remember we've got to go very close. 2.1, 1.9. Negative 2.1, negative 1.9. I'm going to write down what the function is here. It's 2x cubed over x squared minus 4. That's the function. 2x cubed over x squared minus 4. Look, I'd be happy just, you don't have to, you can work it out if you want. 2 times 1.9 cubed over, look, 1.9 squared is less than 4. This is positive over negative. It's negative. If someone wants to work it out, they can. And then if I've got 2.1 here, that will be positive, but 2.1 squared is bigger than 4, and that will be positive. This is undefined. It is going to be a negative bigger value as well. If someone wants to just do one of them, maybe, do the 1.9. And this one, the 2.1, that will be negative, this one, and that will be positive. And that's undefined. Sorry, I shouldn't write dash. It's undefined. Undefined. That's negative. That's positive, negative, positive. Anyone got some values or no? Anyone want to work one out? Can someone do 1.9 and someone do 2.1, please? Just do the positive ones. See, what you do, when you do 2.1 squared, it's bigger than 4. So the denominator will be positive. You'll know whether the numerator is positive or negative just by substitution. Which one? Is 45? All right, and did someone, and that must be negative 45 then. Did someone do, that's undefined. Did someone do 1.9? Yeah, negative. And that will be positive 35. Okay, so we can see the values are quite big. All right, horizontal asymptotes. Let's go. The limit as x approaches infinity of 2x cubed over x squared minus 4. Now, what will happen here, you don't divide through the highest power of x. You divide through by the highest power of x in the denominator. Say you forgot how to do these limits. Let's say you decide to divide through by x cubed. Watch. This is the error. So limit as x approaches infinity, and let's say you divide through by x cubed, the highest power, full stop. You won't be able to solve it. Look, 2x cubed on x cubed is 2, isn't it? Over x squared on x cubed is 1 on x minus 4 on x cubed. Now that is 2 over 0 minus 0. That's undefined. If you divide through by the highest power of x, you're going to get 2x cubed on x cubed is 2. X squared on x cubed is 1 on x. You okay? And minus 4 on x cubed is minus 4 on x cubed. When you put limit as x approaches infinity, you get 0, 0. You're not allowed to divide through by 0. So you don't divide through by the highest power of x full stop. You must divide through by the highest power of x on the denominator, which is to divide through by x squared. Got it? So that's limit as x approaches infinity. What do I get if I do 2x cubed on x squared? I'll do it. I get limit as x approaches infinity, 2x over 1 minus 4 on x squared. And when I substitute my limit as x approaches infinity, I'll get 2 times whatever x is over 1 minus 0. Now, this is a y equals, by the way. When you do limit, your horizontal asymptote is a horizontal line, which is always of the form y equals. So I get 2x over 1 minus 0. Your horizontal asymptote is the line y equals 2x. Because let's say I substitute in x is 100, I'm going to get 200 here. So we're going to draw it now. I'm still going to do, even though I'm doing this limit, you need to know whether you're approaching above or below the line y equals 2x. Okay, so we're going to start sketching. I still would like to do some substitutions. Just, can you do when x is 10, what y is? And when x is negative 10, what is y? What do you get? X is 10. See how that's approaching from above 2x? It's a bit more than double. See how that makes sense with y equals 2x is the asymptote? When x is 10, you get 20.8. It's coming from above 20. And when x is negative 10, what do you get? So it's coming from below 2x. Okay? So let's draw. Asymptote at negative 2. I have a feeling this is an odd function. I think it's an odd function, girls. So 2. remember we've got 0, 0, what do we have? An inflection, don't we? And we can see at 0, 0, looking at this, you can see the shape of the curve. Concave up, concave down. Concave up, concave down. You know that when x is negative 1.9, x is negative 1.9, positive 35. When x is negative 2.1, x is negative 45. So we know that when x is negative 1.9, it's very positive. Also, I'm looking when x is 1.9, it's negative 35, so it looks like this. You got that bit? Now, I'm going to have to put in an asymptote. Oops. Whoops. I know that I'm going to draw, ladies, that's my, remember it's not to scale. Shh. That's my oblique asymptote, the line y equals 2x. Okay, now let's start sketching up here. I know that when x is a little bit more than 2, for example 2.1, y is positive 45, so I'll just say it goes up here. It approaches there. I also know that I've got a minimum turning point at 2 root 3, 6 root 3. So 2 root 3 we said it was about 3.4. I've got a minimum turning point. I'm just going to go like this. And then it approaches from above. For example, when x was 10, I got 20.8, which is above the line 2x. So this is what I've got. Oops, just not drawn very well. So you need to put that this is a minimum at 2 root 3, 6 root 3. Okay, and this is my oblique asymptote, and the curve approaches that from above. Because when x is 10, it's 20.8, so it's above that line. Then back down here, we know that when x is negative 10, it's negative 20.8, so it's below. And this, we know that when x is negative 2.1, it's negative 45. And we know where the maximum, we had a maximum here at negative 2 root 3, negative 6 root 3. And that's the curve. Here you go. Now that is the worst of the obliques in that exercise.